Hello everyone, good to see you again. Last time, following the demo and tutorial, we installed BIND9 on Kali Linux and performed some quiet reconnaissance. After that, I kept reflecting because Matthew said we need intelligence-driven mindset. The goal is how to survive inside a system and take control of the whole network. Matthew designed this lab with DNS as the first lesson, teaching us to first draw the blueprint of the entire building. We just stare at the lock on the front door. And that's how real red teams operate. Stealth, recon, lateral movement. These matter far more than just dropping a payload. Earlier, I took many courses in China, IPs and server roles from the protocol layer. You have the target's IP and domain default, and you just start attacking the web interface directly. But Matthew's first lesson is, if I don't know what's inside your internal network, how do I even start? SQL injection, solve stealing data from databases. What we do with DNS zone files, solve stealing internal. In a real attack, if you only focus on the web, you might spend months without ever getting in. But if you use DNSSEC or sub-U domain brute forcing to obtain the internal network layout, you might hit the core server in one shot. Local training aimed at fast employment often only teaches SQLMAP and burp suite operations. But Matthew, even with a simple dig command, makes us open the named.conf file to read the source and write our own zone files. If you only know SQLMAP, you'll panic when a WAF blocks your parameters. But if you've written bind zone files and understand underlying configuration, even if you switch tools or have none at all, you can still sniff DNS information through protocol handshakes. Over the past few days, I've been thinking that this lab system shouldn't be just about bind. So I dug deeper and found many more surprising elements. Not just what we've covered, but things worth exploring and pondering on a deeper level. He also mentioned that we shouldn't be mere copy or paste learners. We should think about each step and what lies behind it. That's truly valuable. Now, let's jump straight into my virtual box and start the hands-on work. I open my virtual machine and start the HackerHouse Lab ISO. We arrive at the main interface where the internal IP has been automatically configured. At the bottom, we see the login prompt. We already set the credentials when creating the VM, so I won't type them again. Here, after logging in, we enter the nsa.gov prompt screen. This is a lab configuration imitating the NSA, US National Security Agency. Of course, external access is possible, but requires extra setup. We won't cover that today. Now we go to the bind configuration directory, cd, etc. Bind. All bind configuration files are here. The name named comes from name. Daemon, we can pronounce it as named. Then we run sudo nano name.conf. Local and type in the zone. Definition, blocks in nano. We see the zone file includes the configuration for db.nsa.gov. db.nsa.gov. This is a very typical DNS zone file used to define name resolution, mail routing, and security policies for a specific domain. Notably, it contains many IP addresses, starting with the 10th of October 2010. 1. These are private LAN addresses, so this is clearly an internal network configuration file used here for teaching, not a real external DNS configuration. 900 seconds equals 15 minutes. Let's look at the key. Records $TTL 900 global. Default time to live at INSOA. Start of authority. Record. Defining the primary DNS server and admin email. Serial number 2. Refresh, retry, expire, and negative caching TTL parameters. NS records delegate the domain Anycast network. MX records point to mail gateways. TXT records include SPF, DKIM, DMARC, and other security policies. Service NS1, NS2, www, mail1, LDAP, SIEM, VPN, and more. These records comprehensively reveal the internal network topology, mail, authentication security operations, program endpoints, DMZ, all laid out. Next, we restart the service and test local resolution. Now we query with dig.nsa.gov at 127.0.0.1. Let's examine the output. The header shows status. Nowhere and the AAF flag, authoritative answer, proving this server is the master for this zone. The answer section returns 10.1.0.80, matching the zone file. The authority section lists the Akamai NS records. Query time is 4 milliseconds, indicating the server is on the same LAN. These details confirm our configuration is correct. Now we enable this DNS server to resolve internet domains like baidu.com. Edit named.co.nf. Options: add. ACLs allow query and allow recursion to restrict access to. Internal subnets only set. BIND9, listen. IPv6, enable. Recursion, yes. Set forwarders to. To 114.114.114.114.114 and 8.8.8.8 with the policy forward. First, this provides internal clients with external resolution, while preventing the server from becoming an open resolver that could be abused. Restart BIND9. Now, there is no response returned. For convenience, I set up an SSH remote login service so that I can directly log in from my local network. I'll run it on my Mac attack machine. Now, let me open my remote LAN and connect to my server. Okay, we are successfully connected. Let me run the query again. Timeout. Let me troubleshoot this issue. Why is it timing out? Let's go into the configuration file and check the settings. Why is your band DNS server suddenly ghosting you? You type the dig command and nothing. Total silence. Let's into the band server configure path. The culprit lies right here. In these default settings, they look fancy, but in a local network, they can paralyze your server. Trap number 1, DNSSEC, auto-validation. It acts like an overly strict security guard. If your system time is off by a hair, or upstream fails to cooperate, T blocks the response entirely for safety. Changing it to no fixes this instantly. Trap number 2, IPv6. If your network doesn't actually support IPv6, keeping this on sends your server down a dead end. It sits there waiting for an echo until your command times out. Changing it to none forces it back to the IPv4 highway, hides the specific bind version number to prevent hackers from exploiting known vulnerabilities. In a particular version, we cleared the dead ends and skipped the rigid checks. I've already got the file configured. Now let me check the syntax settings. Restart bind server, and then take a look at the status. Okay, everything's normal. I make a mistake. First, let's look at the first section. Here, a forward lookup zone named nsa.gov is defined with the type set to master. This means when an internal user tries to access this domain, the server will bypass the public internet and force load the local db.nsa.gov record file. In cyber range exercises, this is commonly used for DNS spoofing, hijacking specific domain traffic to our custom phishing sites or target machines. Moving on to the second section, this configures a reverse lookup zone. Note that 0.1.10.NADR RPAR is written in reverse notation, which actually represents the internal subnet 10.1.0.0.24. Its purpose is to map IPs back to domain names. The server pulls the pointer file db.nsa.gov.nv and returns the spoofed domain. In network penetration testing, this is frequently utilized to confuse admin log audits or bypass host-based reverse DNS verification. Now we are inside the db.nsa.gov zone file. The first section defines the DNS infrastructure. Here we see two A records, mapping the primary name server NS1 to the internal IP 10.1.0.50 and the secondary NS2 to 10.1.0.51. This builds a completely spoofed authoritative DNS architecture within the victim's network. Next is the Public Web Services module, which deeply simulates the Akamai CDN edge node architecture. The root domain @ is simultaneously mapped to the internal IPv4 address 10.1.0.80 and a spoofed IPv6 AAA address. Meanwhile, the www, portal, and web domains are seamlessly redirected to this predefined web node via CNAME alias records. Moving on to the mail transport module, which is configured as an internal authoritative view. As we can see, all core assets including Mail1, the mail gateway, and webmail are mapped to the 10.1.0 X private subnet. In a cyber range scenario, this completely reproduces the closed-loop traffic of internal mail routing and gateway filtering within an organization. Looking further down, we have the configuration for identity verification and directory services. Here, auth and lab point uniformly to management servers around 10.1.0.90 and directory services via a CNAME record. In a live production environment, this centralized resolution ensures both the physical and logical isolation of internal authentication traffic.